This section explains the two ways a quantum field theory computes a single object, the amplitude to pass from one field configuration to another. Canonical quantization promotes the classical variables to operators, postulates the canonical commutators, and lets the Hamiltonian drive time evolution. The path integral builds the same amplitude directly as a weighted census of every trajectory, each one carrying the phase e to the is over h bar. These are two languages computing one object. Their equivalence is the spine of the chapter. The book will later speak whichever language a given problem rewards, never committing to just one. And the classical world is not thrown away. It is recovered. As h bar goes to 0, the phases thrash and cancel, leaving only the stationary trajectory, and the Euler-Lagrange equations re-emerge as the lone survivor of destructive interference. Quantization, then, is least action generalized from a single path to a sum over all of them. This section explains what quantization does at the base of the whole subject. A classical field is a Lagrangian obeying least action. Quantization is the single operation that turns that datum into transition amplitudes, and it comes in two equivalent presentations. In the first, you promote the field to operators and impose canonical commutators, letting the Hamiltonian generate time. In the second, you sum e to the is over h bar over every history, the path integral. The equivalence is the step that does the work. You pick the language, the problem rewards, and metaphysics gets no vote. The classical law returns for free. As h bar goes to 0, the integrand oscillates wildly and only the stationary, least action path survives. This is Chapter 1's contract with the book. Everything downstream is this same operation applied to richer Lagrangians. This section introduces the idea of renormalization. What you measure is always a dressed parameter, the bare value together with every interaction it cannot escape. You never glimpse the bare parameter on its own. The chapter's anchor is deliberately mundane. An electron in a crystal has an effective mass, written m star, that differs from its free mass m because the lattice pulls on it. This is wholly classical, with no infinity in sight. Renormalization is just the recognition that this dressing is universal. Relativistic field theory adds two twists. First, the shift is infinite. The loop integrals run to unbounded momentum with no natural cutoff. Second, you can never switch the interaction off to glimpse the bare value at all. So, the move is bookkeeping. Let the unmeasurable bare quantities absorb the infinities, and every measured quantity emerges finite. This section explains renormalization as a structural primitive. Renormalization is often mistaken for a trick that deletes infinities. The truer reading, you never observe a bare object, only the object dressed by an interaction you cannot switch off. An electron in a crystal responds with an effective mass, written m star, that is not equal to its free mass, m. The lattice shifts it. The move is this: assume the unmeasurable bare parameters already carry whatever divergence is needed, so the interaction's shift cancels against them and leaves the observed quantity finite. The boundary reveals the structure. In the crystal, you can weave the lattice and measure both masses, and their difference is finite. In relativistic field theory, the field cannot be turned off, so the shift is infinite. Yet the logic is unchanged. This section explains the renormalization group, the subtraction point where you fix the mass, and the coupling is arbitrary, pure bookkeeping, chosen rather than measured. Physics cannot depend on it. That is the whole chapter, and it wears the face of a tautology. Its force is that a redundancy you were free to impose becomes a constraint the theory must obey. The transformations relating one scheme to another compose and invert, forming a group and demanding invariance under them, which is the Callan and semantic equation, pins how Green's functions run with energy. Here is the surprise. A convention promoted to a symmetry dictates asymptotic behavior. Scale dependence is the shadow of a choice you insisted must not matter. This section explains Chapter 3 of the book, whose title, Three-Body, points away from what it actually covers. The real subject is the renormalization group. Its thesis is a single structural move, an arbitrary choice that physics must be blind to becomes a symmetry. Where you subtract the divergences which point in momentum space fixes the mass and the coupling is pure convention. The bare Lagrangian is 1. Demand that measurable content ignore that choice, and the near tautology tightens into a real constraint. The coupling must run with scale, its flow set by a differential equation. This is the same pattern as gauge freedom, a redundancy in description, promoted to a group whose invariance is the physics. What looked like bookkeeping latitude is the theory telling you how it changes with energy. This section explains how symmetry organizes matter before any dynamics enters. A group is the abstract shape of a symmetry. Its irreducible representations are the indivisible patterns that shape can act on, and the chapter's whole wager is that particle multiplets are those irreps read straight off the group. Fix the group as SU3, acting on 3 quark flavors. Then every hadron becomes a tensor power of the fundamental triplet, decomposed into irreps. The fundamental triplet tensored with its conjugate, 3 tensor anti, 3 tensor anti, 3 decomposes as 1 plus 8. That hands you the meson octet with no force law written down. A particle is defined by how the symmetry moves it, not by what it is built from. The symmetry here is global. The same machinery made local becomes the gauge interactions of Chapter 8. The book's real destination. This part explains how symmetry turns into a computational tool, and why Chapter 4 installs that tool before Chapter 8 needs it. Symmetry becomes computational the instant you name it a group. The operations that leave physics invariant compose, invert, and associate, so the full apparatus of Lie theory applies to them. The payoff is representation. States are vectors that the group rotates among, and an irreducible representation is a family that no symmetry operation can escape. This is why particle multiplets are not a list to memorize. They are the irreps of SU3 flavor, and the quark model is simply what falls out of asking which indivisible families the symmetry admits. Chapter 4 installs this global machinery, SU2, SU3, and the tensor methods, deliberately ahead of Chapter 8. There, promoting symmetry from global to local turns the same move from classifying particles into generating their interactions. This section explains why the light quarks are treated as massless and what that masslessness forces on the strong interaction. The light quarks owe their lightness to something structural. On the strong scale, they count as massless. A massless quark has left-handed and right-handed halves that rotate independently, and that independence is chiral symmetry. Yet no mirror, doubled, degenerate hadrons appear in the spectrum, which naively kills the symmetry. The chapter's move resolves this. The symmetry is exact in the Lagrangian, but broken by the vacuum itself. That reversal is the whole content. Its receipt is the near massless pion, a Goldstone boson, the ripple that a hidden symmetry always leaves behind. So you read the spectrum backwards, the absent parity doublet together with the present pion, diagnose a symmetry realized in Goldstone mode. This is the fingerprint that any theory of the strong interactions, QCD included, must later reproduce. This section explains a single structural idea, a symmetry. The Lagrangian keeps, but the vacuum refuses to share. That is the chapter's one primitive. The light quark masses vanish on the strong interaction scale, so the true exact limit is chiral, the group SU2 left times SU2 right, not merely equal masses. Yet the spectrum shows no parity, doubled multiplets to match it. The resolution is that the symmetry is spontaneously broken, realized in the Goldstone mode rather than the visible one. The unpaid degeneracy is refunded as near massless bosons, the pions, the pseudoscalar octet. From here, current algebra extracts real predictions from bare commutators and conservation laws. What the chapter is for, any theory of strong forces, QCD included, must carry this hidden chiral symmetry. This section explains what renormalization does to symmetry, taking the usual relationship and turning it around. Start with the classical picture. A classical symmetry constrains the Green's functions, and those constraints are the Ward identities. Renormalizability leans on them. Divergences coming from separate sectors cancel only because the identities force the cancellation. The chapter inverts the question. The classical question asks whether symmetry protects renormalization. The chapter asks the reverse. What does renormalization do to symmetry? The answer is that quantization is not neutral toward it. Two directions show this. The vector Ward identity survives one loop, but the axial one cannot. The triangle fermion loop forces an anomaly, a symmetry exact in the Lagrangian yet broken by regularization. And in the reverse direction, radiative corrections can manufacture a spontaneous breaking that the classical potential never carried. The primitive is this. Symmetry is a property of the action that the loop expansion may rewrite rather than simply inherit. This section opens the arc on how quantization tests classical symmetry. A classical symmetry is only a hypothesis about the quantum theory. The loop integral is the arbiter of whether it survives. Symmetry stamps itself on Green's functions as Ward identities, and the renormalizability of any non-trivially symmetric theory rests on those identities, forcing the divergences from separate sectors to cancel. This chapter inverts the usual reading. Instead of asking what symmetry does to renormalization, it asks what renormalization does to symmetry. Three answers set the arc. First, a conserved current passes through untouched, its renormalization constant z equal to 1. Second, an axial symmetry is broken by quantization, the anomaly, which then predicts the neutral pion decaying into two photons. Third, radiative corrections can manufacture symmetry, breaking that was absent classically. Symmetry is never inherited for free. This part explains the Parton model and scaling. Fire a hard enough lepton at a proton and the response stops caring about how hard. The structure functions collapse onto a single dimensionless ratio. X, instead of depending on energy and momentum, transfer separately. That vanishing of scale is the signal. A probe that resolves no characteristic length is bouncing off something with no size. Feynman's reading turns the puzzle trivial. The proton is momentarily a swarm of nearly free point-like spin, one-half constituents, the partons, and X is just the fraction of its momentum the struck one carries. Scaling and structurelessness are the same statement. An incoherent elastic hit on a point has no scale to break the ratio. This is where quarks stop being bookkeeping and become something you can scatter off. This section explains why bombarding a proton hard enough reveals that it is made of point-like pieces. Bombard a proton hard enough, and its response stops caring about how hard. The structure functions collapse onto a single dimensionless ratio, rather than depending on energy and momentum transfer separately. That scale, blindness, is Bjorken scaling, and it has exactly one honest reading. The probe is bouncing off something point-like. A target with intrinsic size imprints that size on the cross-section. A structureless one cannot. So the smooth proton, resolved finely enough, is a swarm of nearly free spin, 1/2 granules, Feynman's partons, which the chapter identifies with quarks. Here is the generative move. Absence of a scale in the answer means absence of a scale in the thing. Resolution exposing granularity. This section explains how interaction arises from making a symmetry local. A global symmetry costs nothing. Rotate every point's phase together, and the free Lagrangian never notices. Now demand that the rotation be local, chosen independently at each space-time point, and the derivative betrays you. Comparing neighboring points now compares different frames, and an uninvited term appears. The only repair is a field that transports the frame, the gauge field, folded into a covariant derivative. Its coupling to matter is not chosen but forced, and universal, fixed entirely by how each field transforms. This is the chapter's whole move. Interaction is the price of promoting a global symmetry to a local one. The abelian U1 of quantum electrodynamics is the prototype. The non-abelian Yang-Mills case pays more because the gauge field must then couple to itself. This section explains how local symmetry generates the fundamental forces. A global symmetry costs nothing. Demand instead that it hold locally with the phase chosen freshly at every point, and the ordinary derivative breaks it. The chapter's whole thesis is that the repair is the physics itself. Introduce a compensating field whose transformation exactly cancels the leftover term, fold it into a covariant derivative, and what you have done is derive an into a covariant derivative, and what you have done is derive an interaction. Rather, Song's thesis is Daytine. Electromagnetism falls out of free Dirac fermions this way. You never posit the photon. You are forced into it. The generative move, force wrung from insisting that a symmetry be point-dependent, regenerates every case. The one folk to hold is this. When the group does not commute, the compensating field carries its own charge and interacts with itself. This section explains why quantizing a gauge theory forces you to divide out the very symmetry that built the forces. A gauge symmetry is the same physical state written infinitely many times. It adds no new physics. Chapter 8 built the interactions from that redundancy, and quantization now has to pay for it. The path integral sums over every field configuration. But configurations related by a gauge transformation are one and the same state, so each state gets counted once for every point of its orbit, an infinite overcount. The free field operator inherits this. It projects onto the true transverse modes, it has no inverse, and the naive propagator diverges by the volume of the orbit. The whole chapter is one move, integrate over the quotient, the field space with the redundancy already divided out, rather than over the raw field space. Fix the gauge and factor the redundancy away. The symmetry that generated the forces is exactly what you must divide out to compute with them. This section explains why gauge theory forces a single structural move before it can be quantized. Gauge invariance is redundancy wearing the mask of freedom. The gauge field a mask of freedom than the system has. True degrees of freedom, and any two configurations linked by a gauge transformation are the same physics, a single orbit. The path integral sums blindly over every configuration, so it counts each orbit once for every point along it. It therefore diverges by the orbit's infinite volume. Said the other way, the free kinetic operator is a projector onto the transverse directions and has no inverse. Its determinant, the determinant of k, is 0, and the Gaussian trick collapses. The chapter's whole task is one move. Quotient out the orbit, fix the gauge, and integrate over the physical base rather than the redundant fiber. Everything downstream, the ghosts and the ward identities, is the price of that quotient. This session explains how quantum chromodynamics falls out of a single gauge move applied to color. Take the one move that generated electromagnetism. Demand that a phase you can rotate freely at every point costs nothing and apply it to a 3-valued color charge instead of 1. Local SU3 invariance forces 8 gluons into existence to compensate the rotations. The surprise is that SU3 is non-abelian, so the gluons themselves carry color. The force carrier is charged under its own force. That single fact generates everything. The coupling self-amplifies at long range, which is confinement, no free quark. The coupling self weakens at short range, which is asymptotic freedom. Quarks rattle free inside the proton. Same gauge principle as QED, unbroken, non-commuting, and the whole strong interaction falls out of that one twist. This section explains the whole claim of the chapter in a single figure. One Lagrangian and one number that runs the wrong way. The strong force is a Yang-Mills gauge theory, whose coupling shrinks at short distances. That shrinking is called asymptotic freedom, and among all renormalizable field theories, only the non-abelian ones can do it. That single fact reconciles with the deep inelastic experiments forced on us. Quarks act nearly free inside a hadron, yet never emerge as forced on us. Quarks act nearly free inside a hadron, yet never emerge as free particles theories. QED screens charge with virtual pairs. The Yang-Mills vacuum does the opposite. It anti-screens because its force carriers themselves carry color. This is a paramagnetic vacuum. It is placed before electroweak precisely because no symmetry breaking intrudes here. It is the book's clean first instance of the governing object, gauge coupling as a quantity that flows with scale. This section explains why the electroweak theory begins from a flaw in the older description. A dimensionful coupling that grows with energy. Fermi's GF, the 4-fermion contact term, is never fundamental. It is the low-energy shadow of a heavier particle you integrated out. The chapter's whole move is to run that inference backwards. You restore the missing degree of freedom as a gauge boson, then demand that its symmetry be local. But a local symmetry needs a group, and you do not guess it. The already measured fact that only left-handed fermions carry the charged current, arranged in doublets, fixes the group to SU2 sub L cross U1 sub Y. Unification and renormalizability then follow as consequences of that choice. What the chapter is for in the book's arc is this. The sickness of the old theory is the blueprint for the new one. This section explains why Fermi's theory of the weak force announces the energy at which it must break down, and it does so in the units of its own coupling. A coupling constant that carries a mass dimension is a theory naming its own expiry date. Fermi's 4. Fermion contact term carries a coupling, the Fermi constant that scales as 1 over mass squared. That single fact forces both of the diseases, the chapter diagnoses, the bound that a probability is not allowed to cross. The theory diverges past any finite set of bare parameters. The second is unitarity violation. The cross-section climbs in proportion to the Fermi constant squared times the squared collision energy until, near 300 giga-electron volts, it overruns the bound that a probability is not allowed to cross. The two are one pathology, not two. Bad high-energy behavior at low order is exactly what makes the loop integrals impossible to absorb. The chapter's role in the book's arc is to name the cure before building it. Replace the point-like coupling with a gauge boson that is exchanged between the particles and whose Yang-Mills structure is the only thing that tames the growth. This section explains why the electroweak theory earns the title standard. A gauge theory earns the word standard, not by fitting one number but by draining its own freedom. Chapter 11 fixed the SU2 times U1 skeleton. This chapter shows every low-energy prediction collapsing onto a handful of knobs. Really, the Weinberg angle alone, once fermion universality, forces all neutral current couplings to share it, with rho equal current couplings to share it, with rho equal to 1 falling out of the single Higgs doublet. Here is the surprise that does the work. 3 phenomena that look unrelated share one cause. Flavor-conserving neutral currents, the GIM suppression that forbids the flavor, changing ones, and CP violation all descend from the same quark mixing matrix, the last of them needing a single irreducible complex phase. Predict the adjacent case. Whenever symmetry pins the parameter count below the phenomenon count, one knob buys many independent measurements. This section explains why the model earns the name standard. What earns a theory, that title is its parameter, economy. The Lagrangian alone does not do it. Chapter 11 built the Glashow, Weinberg, and Salam structure. Chapter 12 cashes it out by showing that every low-energy, neutral current process, neutrino-electron scattering, the deep inelastic ratios, all of it is governed by a single unknown, the Weinberg angle, once rho equals 1, is locked in place by the single Higgs doublet. Measure that one angle in any process, and every other cross-section is predicted rather than fitted. The phenomenology is therefore overdetermined. Each new experiment is a redundant consistency check rather than a fresh knob to turn. That collapse, a whole zoo of observables squeezed through one number, is what makes the model canonical, and it is what the chapter exists to demonstrate. This section names where the standard model hides its arbitrariness, and the 3 ways this chapter tests it. Every free number in the standard model lives in one place, the elementary Higgs sector. Gauge invariance leaves its self-couplings and its Yukawa couplings unconstrained, so masses and mixing angles must be inserted by hand. That arbitrariness is the model's soft joint, and the chapter pulls on it 3 ways. It replaces the elementary scalar with the dynamical condensate of a new strong force. Technicolor, the BCS Cooper pair. Higgs scaled up, it lets neutrinos carry the mass the model forbade, and it computes mu to E gamma, a test that gauge invariance survives only when the unphysical would. The chapter builds no new theory. It runs 3 probes of where the standard model rests on choice rather than necessity. This section explains where the standard model admits it is unfinished and the single move that turns each admission into physics. Every selected topic here marks one place. The standard model concedes it is provisional and the move is always the same. Turn a postulate into a dynamics. The elementary Higgs is the prime suspect. Its self-coupling and Yukawa constants are free, so masses and mixing angles are inputs rather than predictions, and the gauge hierarchy has to be fine. Technicolor removes it. The symmetry-breaking scalar becomes a fermion condensate, the very substitution BCS made when Cooper pairs, not a fundamental field, broke electromagnetic gauge symmetry in a superconductor. Massive neutrinos and the muon to electron transition are the other two probes, the minimal model's silences turned into handles for what lies past it. This section explains grand unification. A product is a shattered simple thing. The standard model uses the product group SU3 times SU5 times U5 times U1, the strong force, the weak force, and electromagnetism, each wearing its own separate coupling constant. Georgi and Glashow showed that this product is the broken remnant of a single simple group, the smallest one that swallows a full generation of quarks and leptons, SU5. The three forces are one force. They merely look distinct below about 10 to the 15th power giga-electron volts, where spontaneous breaking splits the couplings apart. The generative move is unification, as embedding the product into a simple group. Its signature payoff falls out for free. Charge is quantized because the electric charge operator becomes one generator of a simple non-abelian group whose spectrum is discrete, the SO3 angular momentum pattern. Abelian U1 alone would permit any charge at all. This section explains why grand unification turns electric charge from a fact you accept into a fact you can derive. The standard model wears three separate coupling constants, and it hands you electric charge as an unexplained brute fact. Grand unification is a single subsumption move. Embed SU3, cross SU2, cross SU2, cross U1 inside one simple group, the chapters SU5 of Georgi and Glashow, so that what were independent inputs become forced consequences of the larger symmetry. The signature payoff is charge quantization ceasing to be something you fit by hand. Because the charge Q is now one generator of a simple, non-abelian group, its eigenvalues are discrete by construction. This is exactly the way SU2 forces spin to be integer or half-integer, whereas an abelian U1 tolerates any value across a continuum. Fewer knobs, sharper predictions. The price is a unification scale near 10 to the 15th power, giga-electron volts. This section restores the symmetry that Maxwell's equations almost have. In vacuum, they are invariant under swapping the electric and magnetic fields. Only the electron, a charge with no magnetic twin, breaks that symmetry. Supply the missing object, a magnetic monopole, and the duality closes. Here is the surprise. One monopole anywhere forces every electric charge in the universe onto an integer lattice. This is Dirac's quantization condition. The electric charge times the magnetic charge equals a whole number, over 2. Existence deduces discreteness. The chapter's arc runs from Dirac positing this object by hand to Hooft and Polyakov showing it need not be posited at all. In a spontaneously broken non-abelian gauge theory, the monopole falls out as an inevitable topological soliton. So grand unification does not permit its absence. This section explains how a single magnetic monopole makes electric charge come in whole number units, and how that same monopole stops being an arbitrary object once you read it through topology. Put one magnetic monopole anywhere in the universe, and every electric charge is forced to be a whole number, multiple of one base unit. This is Dirac's condition, the product of the electric charge and the magnetic charge, and the magnetic charge equals a whole number times 1/2. Charge quantization. which is otherwise just an unexplained empirical fact, becomes a theorem. The instant a single monopole exists. The chapter's deeper turn comes in a non-abelian gauge theory with spontaneously broken symmetry. Here, the theory itself forces the monopole into being. No one inserts it by hand. The Higgs field gives a map from the sphere at infinity onto the vacuum manifold, and that map cannot. Its winding number is the magnetic charge, and the charge is a whole number for the simple reason that windings are whole numbers. The T-Hooft Polyakov monopole is Dirac's monopole. Reread as topology. What looked like an arbitrary source becomes an unavoidable soliton. This section places the instanton. It is the same topological move as the previous chapter's monopole, lifted one dimension and rotated into imaginary time. It is a finite action, Euclidean Yang-Mills solution whose gauge field wraps the three-sphere at infinity into the group with integer winding. That integer is a topological charge, and its mere existence forces the surprise that makes the whole chapter go, a configuration-carrying charge. One is a tunneling path between vacua the naive picture had counted as a single state. So the vacuum is a family, indexed by an angle theta. One Lagrangian secretly encodes a continuum of physically distinct theories. Everything the chapter builds afterward, dissolving the axial U1 problem, conjuring strong CP violation, is bookkeeping on that one degeneracy. This section moves one dimension up from the monopole's spatial knot. The twist now lives in Euclidean 4-space, whose boundary at infinity is a three-sphere mapping into the gauge group. Such maps carry an integer, the winding, also called the Pontryagin index. That integer pins the action to a topological floor. The action is greater than or equal to 8 pi squared times n over g squared, and this bound is saturated exactly when the field is self-dual, when the field strength equals its dual. The field that saturates it is the instanton. The meaning of that field is what the chapter is built to deliver. The winding labels distinct vacua, and the instanton is the least action tunnel between neighboring ones. So the Yang-Mills vacuum is a whole degenerate ladder of states where you might have expected a single ground state, and the Lagrangian secretly encodes an entire theta continuum of theories.